Good morning. If I could have your attention, we'll get started because I do want to get through that name that scenario with you by the end of class. So the reminders are up front. I will show you the exam info on the next slide here. You do have a homework 6 coming in today. Homework 7 is open. Homework 7 has just 7 questions. Very first question is just giving you more practice on paired versus independent to know the difference between those scenarios. We will be finishing the two means, mu1 and mu2, hypothesis testing today, and that's where the homework 7 ends. So after today's class, you can try any of the homework 7 questions. Let's see what else. It will be the last homework on the exam. So we'll be finishing through page 166 today in our notes, and that marks the end of material for exam 2. Pages 63 will be the start. That goes back prior to where you had the exam 1 happen. Page 63 is where we first started learning about statistics and having a sampling distribution, and our first confidence interval and hypothesis test for a proportion. So we'll start back at that, and you could be asked about a single proportion, but you could also be asked about two proportions, means, mean of the differences, and difference between two means, those 5 scenarios. So it really focuses on chapters 9 through 13, which we now, after today's class, will have covered all that material. The review will be on a Tuesday before the exam, Tuesday evening in MLB 3. We'll have those review questions up sometime next week for you. Yes, we'll have some new material next week. I will guarantee, though, every lecture will have something for review in it, and the exam week will always do some review in class, both Tuesday and Thursday. All right, questions or comments at all before we turn to our material for today? Any question or comment? All right. We're going to recap that confidence interval about that word color test that was on page 155. Remember, we had you try a couple of these where you had to state the display color. These were the results for an experiment, and we had only this summary of the 2 sets of data, 16 observations in each. We looked at those 2 sample standard deviations, and we said those are starting to look a little bit more different than the first example we did, maybe leading us to say maybe we should do the unpooled technique. So that's what we did the first time. We created the unpooled confidence interval for estimating the difference between our 2 population mean times to complete this task. And the interval did not have a 0 in it, we noted, to show that there was a significant difference between the 2 population means, that the alcohol had some effect. Now your homework has you do an unpooled confidence interval also. So work through that one more time there. This will be a good one to look at for guidance. We turn to the next page, and it talks about what if the researchers who knew a little bit more about this type of a study and these variables and such were convinced that the variances for the populations could be assumed to be equal. And so they had you go through and do the pooled confidence interval instead. So rather than working through the whole thing together, it is all laid out there. Notice there's a couple steps. You have to first get that thing called SP. That's our estimate of that common population standard deviation. That's the first step. If there is a common population variance or standard deviation, let's use the 2 S's together to estimate that. I know on some exams I've seen asking for just the estimate of that common population standard deviation, and students go to the next bullet and give me the full pooled standard error. But estimating the common standard deviation is just that SP, which is used to work out that updated or pooled standard error. When the sample sizes are balanced, equal, here both 16, then it turns out with all that work that the standard errors, pooled or unpooled, end up being the same algebraically. So it's still 6.41. But where do we gain by doing the pooled technique here? We get to use the full total degrees of freedom of 30. When we did the technique unpooled, having only our set of data here and no output, we had to use the smaller of the 2 degrees of freedom. We had to use 15 degrees of freedom only. And now we get to use 30. So that gives us a smaller t star and a narrower interval. So the interval estimate can be a little more precise, still at a 95% level of confidence. Also still excludes a value of 0. So we reach the same conclusion. So that's just a contrast and one place where you'll see the steps for getting SP calculated. We'll do that once today too with a testing problem. Pooled versus unpooled. We'll typically give you a couple indicators for checking which method you should use. So let's try that out with a couple more examples as we lay out how we're going to do a testing of hypotheses. We've already been doing that somewhat by looking to see if zero's in our interval. We're informally testing the hypothesis. Could the difference in those population means be 0? So let's think about that hypothesis testing side. Page 158. 159. The background again is we have 2 populations from which we've taken independent samples that can be representative of those larger populations. So we need the independence of our 2 samples and each being a random sample. And the model for that response, which is quantitative now, the model for scores, the model for times in each population can be assumed to be normally distributed around 2 different means, mu1 and mu2, which may or may not be the same. These are the minimum conditions needed to do our hypothesis test. And H0 is going to be about that new parameter, mu1 minus mu2. And what would we state in H0? Which would be the status quo or statement of no effect, no difference on average. It would be equal to the value, the null value of 0. We, of course, could write that as mu1 equals mu2. That's equivalent. So it really doesn't matter. The first way just defines the actual parameter, the difference in these population means, and some null value. So that's what H0 would look like no matter what direction we're going to put in our HA. Our alternative theory, depending on what group 1 and group 2 represent, might be looking for a greater than 0, which would support that the first population mean is larger than the second. It might be that we're looking for less than 0. It depends on which is group 1 and which is group 2, and do you want the response to be higher or lower to be better? So you have to kind of reason that out. And then, of course, you might be looking for just some change, some difference. I think in one of your homework questions for homework 7, it talks about wanting to compare 2 different routes for going to work and wants to know which one will be faster on average. There's no preconceived notion of which one might be, just want to know if there's a difference so you can pick the right route to go. So that would be a 2-sided version. So we'll do a 2-sided test or a 1-sided test. We'll have to calculate some kind of t-statistics since we're dealing with means and we'll only have standard errors, but we have 2 versions of that test again. The pooled or the unpooled. Those are in your yellow card notes. You again have the formula for this SP that's used in the pooled standard error versus the general standard error. And again, the indication of the degrees of freedom. We can go to pooled, of course, if we can assume one more thing about our populations. And that one more thing is what? Equal variance might not be quite enough if that was all that was written on the exam for that answer. Equal population variances. The population variances are assumed to be equal. Equal variances, are you assuming the 2 S's or S squareds are equal? The sample standard deviations or variances? We're assuming the population variances are equal. All right. So how do we decide? You have a little rundown of some of the guidelines again. You know, the sample standard deviations are similar, and we look at those two S's, we're going to go ahead and pool. If the sample standard deviations are not, well, then we're going to step back and take a look. There's one case where pooling is going to be okay when you have different standard deviations and different sample sizes, but if they're in the opposite direction, then pooling can be misleading. We're going to have a couple indicators to help us. We'll have the S's, we'll have the Levine's test perhaps, or box plots, or even just state, conduct the pooled t-test, because the researchers feel with all the looking at the results that it's reasonable to assume pooling. So we'll have some guidance. We're going to try to pool when we can. So today we'll get through two examples where we again can make that assessment. And the first one is the longer one on page 161 where we have to do some calculations. The second one is much quicker because the output is all sitting right there. We just have to pull out relevant ideas. So let's take a look at our first example on an experiment looking at whether beta blockers help to reduce pulse rate with a group of 60 subjects that are randomly divided up into two groups. And group 1 gets the beta blocker treatment and group 2 gets a placebo treatment. So the statement here of being that there's random assignment, that you randomly divide up your 60 into two groups of 30, that already is indicating that one of our 3 to 4 conditions are met to do a t-test here. What condition does that help us satisfy when we take random assignment of our subjects to the two treatments? Something about the samples. And it's not necessarily saying the samples will be random, because that has to do with whether or not those people represent the larger populations, but rather that the two samples will be independent. Random assignment means I'm assigning them at random. I'm not matching or pairing them up in any way. And so that helps to balance the two groups with respect to other characteristics that might influence the results by the random assignment. So that random assignment is one way to help support that the two samples are independent. That we have two independent samples. Whether each of those samples is a random sample would be based on who are these subjects and can we consider them representing the populations of potential subjects that we want to infer to. All right, beta blocker is group 1, placebo is group 2, the classic setup of data. If this is all you have given to you, there is no way you can do a paired t-test on this, even if there was matching going on, because you don't have the actual differences. If you were trying to do a paired t-test here, you've got the two sample means, and it is true that the mean of the difference is the difference in the means. So you could subtract those and still get the d bar out for the differences averaged. But the standard deviations there cannot be used to come up with the SD that you need for doing a paired design. So if this is all you have to do, it couldn't be a paired t-test that I could ask you to complete, only an independent samples one. All right, we do have some data here. We've got the sample means. Does it look like descriptively the treatment was helpful in reducing pulse rates on average? 65 versus 70. And then we have two standard deviations over here too. Now the first step, of course, is to state the theories that we want to test. That's where we'll have a clicker question for your choice in part A. So think about what the hypotheses will look like. You have those three options. Just have to keep in mind which group is group 1 and which group is group 2. And then you're measuring pulse rates and you want pulse rates to be reduced. You're hoping the treatment will help them be lower. So it's pretty easy to work that through. On your paired homework, you have to be careful how the differences are defined. What was that recycling one again? It was before this recycling program minus after? If the program was helpful, do you want Which one do you want to be higher? Before the program was put into place or after in terms of amount of items recycled or material recycled? You want the after to be higher. So depending on how the differences are defined, you're going to be looking for either positive or negative type of values. What do we have here? Not too bad. Looking to see if the beta blocker group helps to reduce pulse rates. So I'm looking for a reduction in group 1. I do want a change, and that change should be B, looking for a lower tail test. Now, typically on an exam, this question where you set up your hypotheses could be worth more points than maybe some of the others, because I'll take those points away if you get it wrong initially. But every other point you can earn still by doing the test you said you're going to do. So if you picked the wrong direction, you might lose the 2 out of 2 points for that part, but you could still gain the 4 or 6 points for the rest of the testing problem by doing it with your HA. If you're not consistent back with your HA, you'll lose some more points down there, even though they might be the right answer, because you just have to be consistent. All right, we're doing a lower tail test to the left. And let's take a look at the results. We have to decide which test we're going to perform, pooled or unpooled. We only have one indicator to really look at. It's certainly helpful that the sample sizes are the same, but that's not a requirement for pooling. But it's nice when they are, because then the pooled and unpooled standard error are the same. But I'm looking at those 2 S's. And here would be a wrong answer on your exam. We should do the unpooled technique because those 2 standard deviations are not equal. That would be not correct reasoning. Those 2 standard deviations there are almost always going to be not equal because they're the sample standard deviations. Even if the population standard deviations underlying those populations are really the same, when I take random samples from those populations, I won't get the same S each time, and they won't always be equal then each time. So what could we say here? What do you think? 7.8 and 8.4? Those are similar. They're comparable. We talked about one rule of thumb, which is kind of what Levine's test does. It kind of takes those 2 S's, actually the S squareds, and puts them in a ratio. And whenever one is more than twice the other, then you're starting to get a little worried about pooling, being okay and sticking with the unpooled. But here, S1 of 7.8 is very similar to S2, the second standard deviation, which is 8.4. They're comparable in magnitude. If I had 7.8 and 22 or anything large like that, then I'd start to say that doesn't look reasonable, and I would go back to unpooled. They're similar, so we're going to say pooled. So that means performing the actual t-test in Part C requires a bit of work. That's why we have lots of space there. We're going to do the pooled t-test. So what we need is a t-statistic, which on top will look at the difference in the sample means and compare that to 0, which we can easily plug in. But the bottom needs that pooled standard error. And that pooled standard error has that SP in it, which we don't have yet. And it has the 2 sample sizes, both 30. So the first step I need is to get that SP. That formula is on your yellow card. Use it so that you don't drop a square root or forget a square or something. It says to take the degrees of freedom as your weights times each of your sample variances. And just as with your regular S, the quantity on the bottom is your degrees of freedom. Your regular formula for S has n minus 1 on the bottom. That's your degrees of freedom. So I have 30 observations. It really could be just adding the 2 S squareds up and dividing by 2 because they're equal sample sizes, but I'll just plug everything in. And what do I have to do to 7.8? I need to square it. Can be easy to forget to square. Can be easy to drop the big, large square root along the way. If I forgot to do the large square root along the way, I would get underneath that square root 65.7. And 65.7 doesn't look reasonable as an idea of S, a pooled S, between 7.8 and 8.4. If If you take the square root of 65, you will get an answer that's much more reasonable. 8.106. Carrying it out a little bit. Isn't that a reasonable answer for pooling the two s's? Actually the s squareds, but then taking the square root. So take it back to your two s's, make sure you fall in between. So that is a reasonable choice. It would be closer to one or the other if you had different sample sizes. So with SP calculated, that takes a little side work. Let's now get our t-statistic. Our measure of how many standard errors apart our two sample means are. 65.2 is different than 70. It's below 70, as we had hoped. But we'll work out how many standard errors below. It's nice when the sample sizes are the same, so this 1/30 part can be worked out a little easy. But here's where I would show maybe the top and the bottom. Difference of 5.1 on top, negative 5.1, and the pooled standard error turns out to be 2.09. So our t-statistic is negative as we had hoped, 2.44. I get a negative t-statistic, and I am doing a lower-tailed test. That's what I hope will come up. Our two sample means were almost 2.5 standard errors apart. The first sample mean was nearly 2.4 standard errors below that second sample mean. That's how far apart they sat. Does that look like it's a pretty good distance apart? Is being more than 2 standard errors apart somewhat significant in general? Yeah. So let's see how significant by finding our p-value. So let's work out the p-value for our test so we can make that formal decision at a 5% level. So our t-statistic is negative 2.44. I need a p-value. So I need the distribution or the model for my test statistic under h naught being true, because the p-value is always calculated as a probability under h naught. But every t-statistic has a t-distribution of some sort. And this t-distribution will have how many degrees of freedom here? 30 plus 30, 60, minus 2, 58 degrees of freedom, which, because we're going to have to use our table, we don't have, we'll go to 50, going down instead of up. And the test statistic we did observe was here, over here on the negative side, negative 2.44. The p-value is the probability, assuming h naught's true, that you would get a test statistic as extreme as you did get, or something even more extreme. Look at HA for that direction of more extreme. Here's our p-value. So then we work with our table to do the best we can to report some bounds. I would expect that if you have the output, you'll use it and not give me bounds for the p-value when you can actually work out the exact p-value. And what do we get? With 50 degrees of freedom, we fall in between the 2, 3, 3. And even though that's positive there, I can just put a negative sign in front. Negative 2.33 for your one t-statistic, and the other one is what, 2.58? We're using table A3. And those two give me areas to the left in my degree of freedom of 50 row of what, 006 is the smaller piece, and 012 is the larger piece. And that happens to be the same if you were to use 60 degrees of freedom too. Our tail area is somewhere between this 006 and 012. That's a pretty small p-value. If h naught were really true and there's no effect of the beta blockers on average, well then we would see the results like we got, or more extreme, very rarely. Only like 0.6 to 1.2% of the time would you see these kinds of results. That's pretty unusual under that model. Doesn't support that model, h naught being true. So we will do what? What will be our decision? At a 5% level of significance, we will reject h naught. Our actual question here says, are the results statistically significant at a 5% level? And we would say, yes. We have statistically significant results at the 5% level. And what would be our conclusion then? Which should say something about beta blockers, pulse rates, and averages. So, does it appear that beta blockers reduce pulse rates on average? Yes, we have support for that for the population of subjects represented by our samples. So in the populations represented by our samples, we could conclude what? There is sufficient evidence to say beta blockers reduce pulse rates on average. Or that the average pulse rate for beta blocker treated subjects would be significantly lower than the average pulse rate for a placebo group. There is evidence or support for that theory. All right, that took a little bit of work because we had to calculate. That's pooled standard error. Question? Mm-hmm. Yep, you shade always in the direction of your HA. Less than. Group 1, we want it to be lower pulse rates than group 2. What if you had set up your HA wrong? What if you had put greater than in your HA instead of less than? You would have still calculated the same test statistic, I hope, because that wouldn't change. But what would your p-value have been? Not real small, but really big. You take the complement of those two things and say it's somewhere in between the 1 minus of those numbers. Huge. And therefore, you would have circled failed to reject H0 and would have said there's not enough evidence to support that theory. You would have gotten full credit for all of that if you did that consistently with your HA, but you would have lost your 2 points in part A, say. All right, take a look at the next page, which will be a lot easier because the output is all there. We're looking at a maze with rats, a particular drug that should help speed learning. 2 groups of rats, 5 and 8. Group 1 is the control group this time. Group 2 is the treated group. How do you know it's independent samples? There's 2 big clues. First big clue is what? Your sample size is 5 and 8. They're not the same, so that couldn't be paired because they'd have to have the same sample sizes to be able to calculate differences. And the other big clue is right there in your output because it says here's the output for conducting the appropriate test, and it says independent samples right there. Group 1 is the control group. They're going to go through a maze. We want to see if the drug speeds learning, helps them to go through the maze more quickly. We're doing the test at a 5% level. So we need an H0 and HA again. If it's independent samples, I want to see a mu1 and a mu2. And if there's not a 1 and 2, if it's male and female, you can use F and M or whatever. But I want to see 2 population means in that H0 and HA. If it is a paired design, I don't want to see 2 population means. I only want to see 1, the mean of the differences. Okay? To keep those 2 scenarios separate. Here, we'll have, of course, the standard H0, that mu1, and we can put the equal in between if we want, is equal to mu2. No difference between the 2 groups in terms of their times going through the maze on average. What do I want for HA? All right, so group 1 is control. Group 2 is the treated group. Group 2 should be able to have learned and be able to go through the maze more quickly. So their times should be less, faster, smaller. So I want group 2 to be smaller and group 1 to be larger. So that tells me the direction to put in between. A little tricky sometimes when it's times, because sometimes it is the smaller numbers that are better. So it will be a greater than, and that's primarily why the group 1 was called control, just to be able to maybe work with positive numbers rather than negative ones. All right, so now we just have this test statistic line and this p-value, and we've got to pick. And there's actually 3 different p-values up there. And there's 3 different test statistics, but we got to pick the right one. The first thing we need to do is decide which of those 2 rows in that bottom part of the output am I going to use to pull off my t-statistic and my p-value, the pooled or the unpooled, the equal variances assumed or not assumed. So I have 2 signs in this one, 2 indicators. One would be what? I'm going to compare which 2 numbers on the top? The 2 standard deviations. I remember this exam question when it was in an exam before, and I had students compare the 2 standard errors, which would not be correct here to do because the 2 sample sizes are different. So they won't be reflecting the same kind of information. You don't expect those to end up being the same if you had different sample sizes, even if the S's were similar. So we have to look at the standard deviations. That's 3.4 and 4.8. That's not looking too bad. And what about another indicator, which happens to be one of those other p-values sitting there, and another test statistic, which we haven't quite learned about yet. But there's another example, that Levine's test, which you'll see in the video you watch for your pre-lab 7. You'll be able to do one more example, pulling that out in labs next week. It's the Levine's test for equality of variances, equality of the population variances. There's the H0, HA test for can we pool or not. And it's that p-value that's sitting there, that observed significance, that I see is pretty large. This p-value being greater than 10%, which is the usual level for doing this type of test at. We want to be able to pool if we can, and we'll be a little more relaxed and let alpha be 10% here. So we'll compare that to 10%, and it's bigger. If that p-value is big, I stay with H0. If I stay with H0, I'm staying with that statement of equality of variances. So if the p-value is big, that indicates that we can pool. So we've got 2 things going for us. We've got the 2 S's that are similar. We've got this large p-value for the Levine's test that helps to indicate pooling looks reasonable in this scenario. So that tells me which row in the output under the t-test for checking if the means are equal, which is the test I'm asking you to report here. Now we know which t-statistic to write down. Which one? The 3.4 or the 3.7? I want the equal variances assumed, the pooled test to be conducted here. And that p-value is 0.341 without having to calculate SP or anything else like that by hand. I have had some students still calculate all of it. They work out SP. I don't give them enough space on the exam to even do all that. They do no need to because it's already calculated there. You do have to do one thing, Mo, still with your p-value. Is our p-value 0.006? Nope. It's got to do something with that because this is a 2-sided p-value and I'm doing a 1-sided test. Take a moment to look and see what direction were you looking for in HA? To the right. What kind of t-statistic did you get? Greater than, positive. Good, I'm on the right side. I was hoping for greater and I got a positive t. So that means I can do what to get my p-value? Just cut it in half. If you need to draw the quick picture to make sure you're doing the right thing, that you haven't missed, where you maybe should take a 1 minus, go ahead. The picture, though, would show a 3.41 and a little tiny tail area to the right, which must be really small. So there's our p-value. And therefore, our decision is what? This is, again, that rule that you better not mix up and get backwards, because now it'll happen about 3 or 4 times on your exam, not just maybe once. We should reject H0 and write out a conclusion. What can we say? Thus, the population mean time to complete the maze is significantly lower for the rats taking the drug. As compared to placebo, we should maybe put here. Or there is enough evidence to say that the drug speeds learning on average for the population of rats that our samples represent. I'm laughing because I had mice in my conclusion. It's about rats. All right. That one didn't take as long because there wasn't hardly any calculations. You would likely be asked to give evidence why you're doing pooled or unpooled, and to cite those values you're using from the output, just as we went through together. Not asked for here, but likely that could be part of the problem. All right, the dark chocolate one I'm going to post for you. It's another good example for you to go through, so try it out. Check your solutions. What we're going to do is turn to our 5 scenarios and start picking the right one for different questions asked. Page 166 has that full part of your yellow card. Look at all the formulas that are there. There's a lot. We do want you to be able to choose the appropriate procedure. Can we take a look at page 164 for just a moment? And then we're going to turn to that name that scenario. I'll give you a break to pull that out and look at it a moment. 13.6 is a short section in the text. It's a good one to read. Question? The example we just went through said test about the means at a 5% level. So that test about the two means being the same or not is done at a 5%. If I don't specifically give you a level to test Levine's at, the common level used for these pre-tests for checking conditions is 10%. That's fairly standard, so go ahead and use that. Thank you. All right, so here are the 5 parameters, the 5 different scenarios that we could ask you to make a confidence interval for or test a theory about. So they talk about in section 13.6 some good questions to ask, and that should help you figure out the scenario you're in. The big question is, what are you measuring? That, of course, will help you decide if it's proportions or means. Proportions would be when you're measuring and counting how many successes, when it's a categorical response and you're looking at how many are red versus not red. Whereas when it's a quantitative measurement, and even if it's just the number of pets, the time to complete a task, the score on some test, well, then that's quantitative, and that's going to be about the means. Now, chances are you'd see the word mean or average somewhere in the description too, which would be a good clue. In either case, you'll have to see whether you have one set of data or 2. And if it's 2, in some places, at least for the quantitative side, do we have paired or independent samples? So that's why your homework 7, the first question, just has you distinguish between those 2 again. There is a paired proportion problem. We haven't gotten to that yet. It's a chi-square test we'll perhaps see later in the class. So that will come to fill in that missing blank, that little bit of paired data there that's missing. And then it also mentions that, of course, the description of the problem should allow you to know whether we want to make a confidence interval to answer the question or whether we need to do a hypothesis test. Keywords in whether it's a confidence interval would be, I want to estimate the true proportion of all people who would vote yes on that upcoming proposal. I want to estimate. I want to learn what that value is, not a preconceived theory about it. Versus hypothesis testing, there will be some kind of theory that they want to assess, that they want to test, that they want to learn if there's support for the new drug being better. That's a theory being put to the test. All right, so some of the old exams, when you start to look at them, either on the exam 2 or finals, we'll have sort of a name that scenario problem where we just have you figure out what you would be doing, but not necessarily calculate all the details to do it. Just identify what technique would be used. So we're going to play Name That Scenario now. I do have a few copies. If you did not bring yours, you may grab one. We'll take about 2 or 3 minutes for you to look them over. Going. Sorry, I didn't bring one up for everyone. Extras? Couple extras.
Thank you. Thank you.
All right. We're going to take this worksheet and go a little further than just ABCD matching. In each scenario, we'll also ask what the hypotheses would look like if it's a test of hypotheses. We'll have you write down for that test or confidence interval what the conditions would be needed to do that test. So you'll have a good place of some of those conditions as a summary. All right, so we've got Bobby and Barney. They are bakers, and they're thinking about packaging their mini chocolate chip cookies into individual bags and putting them in vending machines. But before they decide to do that, they've got a lot of questions. They have some theories they want to assess. They have some decisions to make in that production and marketing. And for each issue, then, we have to decide which of our 5 scenarios, proportions versus means, paired versus independent, which one's the right one to use to address their research question. All right, so I am going to have clicker questions for these. We're going to pick from A, B, C, D, or E. Let's see how well we do our first time playing this. You get to do it again in labs next week with another set of questions. This is where I think you need the most practice, to be able to just understand the scenario and begin to do the right thing, because otherwise the formulas are on your yellow card to work out those details. So our first scenario, our first issue, is comparing our chocolate chips to cookies to the competitor. The question is the average number of chocolate chips in our cookies higher than the average number of chocolate chips in our competitor's cookies? The choices are the same A, B, C, D, E that you have on your sheet there. That's the question that we want to put to the test. Which method for testing, and this is all testing today, would we use? You're welcome to check with your neighbor to see if they've got the same answer as you. Look for the key words, ask what are you measuring? Number of chocolate chips. If you think you've got your choice done, go ahead and write out what you think H0 and HA would look like. All right, do you see some clues in the question? I hope. Let's see what you're doing. Last call for your answer. And most are correctly guessing C. It is a 2-sample t-test for comparing our 2 means. C will be the correct answer. What tells us that? What do we know why it's means versus proportions? Because there's the word average, and there's another average. There's two averages. There's two means. I'm going to take some of our cookies and for each cookie count up how many chocolate chips are in it, record those values, compare it to another set of data for doing the likewise measurement but on our competitors' cookies. Not matching the cookie here with the cookie here to be matched or paired in any direct case. Could you match in a problem like this? Could you come up with a reason why you might want to? If the cookies vary in size, maybe you'd want to match by size, but if that wasn't described, don't assume something beyond what's given here to address the right procedure to use. So comparing two population means is the correct answer. So if we let 1 represent ours and 2 represent theirs, what would the hypotheses look like? It's a 2-sample t-test, 2 independent sample t-tests. That's what we just finished doing today, right? So there would be a separate mu1 being equal to mu2. And how would you write out the alternative? They want to know if the average number of chocolate chips in ours is greater, higher. Now, what would the test statistic look like? We just worked with that test statistic a few times today. It's going to be some type of t-test. Because we're doing a hypothesis test about the means, it's going to be a t statistic. We actually have 2 different versions we could look at. If we assume that the population standard deviations really are equal, then we're going to calculate that pooled t statistic. And we'll just put the pooled standard error on the bottom. So that t statistic will measure how many standard errors apart the 2 sample means are. As we looked at in our other question earlier today, if our t statistic is a 3, the sample means differ by 3 standard errors, and that's a lot. If our t statistic is only 0.2, our 2 sample means only differ by 0.2 standard errors, not even 1 full standard error apart. All right, this question could be asked for any test you do. You've seen it on homework. What is the distribution of the test statistic under the null hypothesis? Now, sometimes it's put more in the context of the problem, which might be here. What's the model for your test statistic if there is no difference in the average number of chocolate chips? So what is the model for your test statistic? Well, it's a t statistic, so it's a t distribution. To be complete for the model, we should put what? The degrees of freedom. And we don't have more information here, so it's going to be an n1 plus n2 minus 2. If I told you how many cookies of each type I gathered, then I expect you to put the numbers in. You could draw that distribution to find the p-value. That's another way to ask that question. What's the distribution that you're going to use to find your p-value? Because that is the distribution of your test statistic under the null hypothesis. How about that set of conditions? In a 2-sample t-test, I like to think there are 4 conditions for doing the pooled technique. The first condition is about the sample, and that is that each sample is what? What kind of sampling technique do we want to have? We want to have each sample be a random sample. And then what about those 2 samples? They're not matched or paired, they are independent. The 2 samples are independent. That might be by the design of the study. If it were that experiment when you randomly assign subjects to 2 groups, that helps to have that second bullet be met. And then what are those 2 conditions about the 2 populations that we have? One is about the model for those populations. Each population of responses must have what kind of model? Has a normal distribution. Not normal 0, 1 here. The model for the number of chocolate chips in our cookie should be modeled normally with some mean mu1 and some true standard deviation. And likewise, the model for the other competitors' number of chocolate chips should be normally distributed too, around mu2. The last condition for the pooled technique specifically, I've already got it written up there. In words, it might be the two population, either variances or standard deviations, are equal, are the same, equal population variances. There's a few ways of saying this correctly. You could say it with notation or with words, but there are the conditions. And to know how you would check these various conditions, you could be asked to state the condition or to check it. Checking it would mean not you making the QQ plot on the exam, but looking at the QQ plot that's there and using it to make a decision and making sure it's the right QQ plot to look at. All right, so there's number one. Number two. Second question, click it in. We have these two different ways to seal the packages, and we want to know whether or not the percentage of defective seals under the first option is different from that for the second option. Obviously, you don't want the seals to be defective because then the cookies will go stale. So we'll take a bunch of bakes and have them be sealed under the first option. That's a good seal. That's a good seal. Oh, that one's defective. Record whether the seal was a good seal or not. Do the same thing for another set that were fused together under the second option. All right, get your answers in. Doing pretty well. Measuring whether it was a defective seal or not. Comparing two different methods, we should pick E. We should do a test to compare the two population proportions. Exactly. We have option 1 and option 2. Write out the hypotheses, H0 and HA. What would those look like? What's wrong with this? What doesn't go in H0 or HA? The hats, the statistic. What should go there are the parameters, the true values. And what kind of hypothesis HA will we be looking for here? I want to know if there's any difference. So P1 is not equal to P2. Or you could write it as the difference being 0 and then the difference being not equal to 0. That's fine too. All right, the test between two proportions. We did this right before exam 1 happened, but it wasn't covered on exam 1. We would calculate what kind of test statistic. Well, it's in the name of it right here. It's going to be some Z statistic, which again measures how far apart the two sample rates are in terms of no standard errors. What we had downstairs here was this common p hat, if you remember, and that 1 over n1 and 1 over n2. Now you've got that formula right on your yellow card. But if you remember, there's a common p hat involved in this problem because if H0 is true, those two proportions in the population should be the same. So there really doesn't have to be a 1 and a 2. There's just some common p. All right, if I'm thinking of a Z statistic, what kind of model do you think about for finding the p-value, for drawing under H0 being true? The distribution of a Z test statistic would be not just normal, but normal 0, 1, the standard normal for the model for our test statistic. Now the model for our population of defective or not defective seals over here won't be normal because each thing I'm measuring is either yes, it's defective or no, it's not. A bunch of yeses and nos. But the test statistic calculated is a Z. And under H0, it'll be approximately normal 0, 1, provided the conditions are met. This is another two independent samples problem. So the first two conditions are the same as what we wrote down on the other one. The first condition should be about the samples being random. Each sample is a random sample. And we do have two samples here. The two samples are independent. We haven't worked with a paired data scenario for proportions yet. Then there's one more. In order to do the z-tests that we learned with proportions, we always had to assume that our sample sizes was large enough. So there's that rule for checking that we have large enough sample sizes, which isn't the 30 or 25 here. That's for means. It is that 10 rule, that at least 10 rule. For a hypothesis test, it's under H0 that I have to expect to see at least 10 yeses and at least 10 nos for each sample. So N1 times the common p hat has to be at least 10. And that first sample size times 1 minus that common p hat needs to be at least 10. I'm not using a 1 and 2 on the hats there, because I have a better idea under H0 that there's this common p, and I use that. Under H0, would you expect at least 10 yeses and at least 10 nos? Same thing for the second sample. That N2 sample size needs to be large enough also. I'm forgetting my at least 10 there. No, there we go. There's our condition for the hypothesis. How does that last one change if you were doing a confidence interval instead? In a confidence interval, there is no common p hat anymore. There's not an H0 saying they're the same. So this would be a 1 and a 1, and this would be a 2 and a 2. All right. That probably is further from our minds. We haven't done a proportion test in a while. We have a third question by Bobby and Barney regarding the two scales that we could use to weigh them. Because, of course, we need to weigh them and make sure they're within specifications before we ship them out. So we're going to take 10 bags and weigh them, each of the 10 bags, on the same scale 1 and scale 2, to see whether the two scales produce different weights on average. What should we do here? We're measuring weight. It's quantitative. Remove the proportion ones. I've got scale 1 and scale 2. Here are the weights. 10 bags, 10 bags. All right. Click in your answers and let's pick the right one. It should be one of the first three because it's weights, which is quantitative, which means means. There's average, keyword. And how are we doing? Most picking the correct paired design. A paired t-test. Why is it paired? It's paired by the bag. You should be able to complete the sentence. Those first two observations under scale 1 and scale 2 are matched or paired by, or the fact that they came from the same bag, or the same person, or the same car, etc. All right, it's a paired t-test. So how would we set up H0 and HA? I will often see the wrong parameter in a paired t-test H0, because you'll have scale 1 and scale 2, and you'll be thinking a mu1 and a mu2. But if it's paired, what do I want to see? Mu sub d. It is true that the average of the differences is the difference in the averages. But you can get mistaken and misled by putting the same symbols there when you're using independent compared to paired. So mu d provides the right guidance that it is a test about the differences. And do they produce different weights on average? Well, H0 would be no difference on average. And HA would be, are they different? Not is scale 1 going to be larger than scale 2, but just are they comparable? Because maybe this is a scale we've been using. Here's a new one that's cheaper, and we want to put that in place instead. Is it comparable to this one that's been calibrated and standardized or whatever? Test statistic here. Test statistic for testing theories about means would be a t-statistic. And there's what it would look like with that standard error in the bottom. If my test statistic was +2, interpret that +2 for me. Not find a p-value for it or use it to make that decision, but what does that +2 mean? That sample mean difference was 2 standard errors above 0. The sample mean difference came in at being 2 standard errors above 0. And that's starting to look somewhat extreme. Distribution for a t statistic under the null hypothesis would be some t distribution. Do we know a little more detail here? What could we put in there? Degrees of freedom for a paired design would be n minus 1. That's what it says on the yellow card. There were 20 measurements made, 20 in all, 10 weights in the first scale, 10 on the second, but there were how many differences? 10. So degrees of freedom should be 9. Your n in a paired design is the number of pairs or the number of differences in your sample. And the conditions required is that sort of checklist of 2, but make sure you talk about that being appropriate on the differences. Number 1, the sample. Those differences. The differences are a random sample from a population of all differences, which has what kind of model? Which is normally distributed. In fact, if you wanted to say what kind of model, it would be normal with that true mean mu d and that true standard deviation, that true mean that I'm trying to learn about and hypothesize about. There's this population with some true mean difference for all the differences that I could have, and I want to learn about that true mean. I would check that normality by making a QQ plot of the differences in my sample to see whether that assumption about normality is reasonable for the population. All right, if you've been keeping track, you can start to weed out which answers are not right anymore, because we're matching, and therefore hopefully pick 1 out of 2 correct possibilities here. And this is where we're going to make sure that our bags are close to that 20 ounces, as they say. So we do sample bags occasionally coming off the production line to make sure that we're doing okay. We don't want to have the bags be underweight, not giving the customers what they should be getting. So we're concerned to see whether or not the average weight is less than 20 ounces. All right, we're going to weigh some bags and see how we're doing against 20. Key word there. A sample, 1 sample, comparing it to 20. So what are you choosing here? I hope the right one. Not 100%, but close. It is a 1 sample test for the mean. We're going to stay for a few more minutes yet and complete these last 2 questions, because then you'll have a good list of assumptions that you can go back to. Can you write out H0 and HA? Let mu be the population mean weight for all such bags produced. Is that true mean weight equal to 20 ounces as it should? What's their concern? What is the theory they want to keep checking their bags that they sample against? Less than. Making sure that they're not underfilling. All right, test statistic here would be another t statistic. We could actually put in the 20 now as the null value. And again, you should be able to interpret that t statistic. I believe it's at supplement number 5 in your bright yellow sheets at the workbook front that has a nice interpretation for a 1 sample t type of problem. I saw someone take that and write out the generic one for each of those cases to be able to just know what blanks need to be filled in correctly. Our distribution here would be what? Some t distribution with n minus 1 degrees of freedom. And now we would have the same 2 conditions as we did on the pair design, but we're not talking about differences here. We're just talking about the weights. You could say here the data that we have are a random sample, and the population of all weights has a normal distribution. Some mean mu that we're trying to learn and hope it's right around that 20, and some standard deviation. I don't always have you check whether you have a random sample, although here would be a good place to have you do that. If I took 30 bags coming off the production line and weighed them and used the results from those 30 bags to test this set of theories, because those bags were produced in a sequence or order, what key graph would you make of those 30 weights? Time plot. And I wouldn't want to see the production process starting to produce a trend, especially a trend that's going down, and hopefully at some point then being below 20. That would be bad. I'd want to see that it's a random sample, that my process is stable, so I could use those 30 bags to assess how I'm doing in terms of average weight. Then there's one left. This one should be 100%. If you've crossed out all the others, there's only one left. We're still concerned about meeting our specifications, so we're going to take a sample bags and just see, does it meet specifications or not? We want to assess if we're meeting specifications more than 90% of the time. So this one has only one more option left, but does it make sense too? I'll sample bags, I'll measure its weight, but I'm going to classify it as meeting specs or not. A yes or no. So the only one that's left is, of course, the test for proportion. 97% of you. I promised my other class I'd do a cartwheel in front of you. Ever got 100%? I haven't done a cartwheel for ages, so I don't know what that would look like at all. All right, one sample z-test for a population proportion. H naught. All about P. 90% is the hypothesized rate. Give me about 3 more minutes of your attention and we'll be done, okay? What should I do for alternative? The true P is what? Greater than. I'm hoping it's more than 90%. If it's less than 90%, perhaps I have to shut down and go investigate where there might be problems. I would calculate some kind of z statistic, which would compare my p hat to 0.9. And on the bottom, I'd use the p naught value of 0.9. You'd have to calculate your test statistic value with z. Now, when can I calculate that z, though? I could only do that if I take sufficiently large sample size. Remember the one on your exam 1 where you went to taking only 10 Ann Arbor adults and only 4 of them said yes or whatever? And that was not a large enough sample size. In order to go to a z statistic and do a z test and use a normal 0-1 distribution for my test statistic, I require that the sample be a random sample. But the z-test requires a large enough sample size. This is not the 25 or 30 or more. This is, again, that at least 10 rule. That sample size n has to be large enough so that if I took n times p naught, the null value, under h naught, would I expect at least 10 saying yes, meeting specs, and therefore also at least 10 not, so that I could actually have some idea of what that rate might be. P naught is there. What would that be replaced by if it were a confidence interval instead? There is no P naught in a confidence interval. It would be P hat. And a binomial test if n is too small. Pictures of the day, there's my boys. I don't show them enough, so there they are. And I hope you have a good day.